The next paper, so the last paper presented by Marie Salm. So Marie, do you want to share your screen?
Hello, everybody. So I will share my screen.
And yes, prioritization of compiled quantum circuit for different quantum computers. So please.
Yes, exactly. So I hope everyone can see my screen.
Yes.
Perfect. So welcome everyone again. My name is Marie Salm and I'm from the Institute of Architecture of Application Systems, and I will present you our work about prioritization of compiled quantum circuits for different quantum computers. And so first of all, I will give you a small introduction, then I will present you our identification of quantum metrics, our approach, the system architecture, and also some results. And then I will finalize the presentation with our limitations and future work. So well, quantum computing is promising, but they are still error prone and only support a small number of qubits. However, the number of quantum computers still increases. And this means that they all differ in their hardware properties, but these are important as they influence the execution results. So it's important to select a quantum computer with enough qubits and only small error rates, and for your specific quantum circuit that should be executed. And well, simply always choosing the same quantum computer for execution is not recommended, because quantum computers are regularly recalibrated, and this recalibration changes the error rates. And in addition, also the compilation that is required for the later execution changes the circuit size and could introduce further error or gates, which then introduce more errors. And furthermore, existing quantum compilers differ in their compilation algorithms, as the mapping is known to be NP-hard. So furthermore, on top of these requirements, also the computing access is regulated by the cloud providers, for example, by using queues or time slices. And so to consider everything, this requires a deep and versatile analysis of the characteristics of the different quantum computers, the different compilers, and as well as their compilation results, and also the access regulations of the cloud providers for the prioritization of the compiled quantum circuits and the associated quantum computers, targeting the user's requirements, for example, precise and fast execution results. So our first research question is as follows. So what are the relevant metrics for the analysis and prioritization of compilation results of a quantum circuit for different quantum computers? And therefore, we collected a set of metrics by analyzing Qiskit, Forest, Zerg, and PyTigant, as well as the cloud providers IBM Q and Rigetti. And so regarding the compiled quantum circuits, we considered the well-known metrics width and depth, but also the multi-qubit gate depth, the number of operations, the number of different gate sets and measurement operations. And in addition, on the side of the quantum computer, that is then the target for the compilation, we have on the one hand, the hardware properties, such as the average gate errors and gate times, as well as the readout error and also the decoherence times. And on the other hand, we have the cloud provider specific metrics, which are here considering the waiting time. And now, well, yes, now we have all these metrics. Well, we have to retrieve them, interpreting them manually. And so for the prioritization, this requires much manual effort and knowledge for the user. So our second research question is as follows. So how can compiled circuits of a given quantum circuit for different quantum computers be automatically prioritized based on the requirements of the user? And so for the prioritization, we use the well-known multi-criteria decision analysis methods. that are commonly applied in cloud computing, finance, and also other areas. And with these methods, it's enabled us to rank compiled circuits based on multiple metrics, the metrics we collected previously. And in addition, such multi-criteria decision analysis methods also usually use weights that define the importance of different metrics. So for example, here the user can define the importance for the different metrics based on their requirements. But as you may know, the number of MCDA methods that exist is really huge. So therefore, we use a tool called MCDA method selection tool. And there we use this tool to select suitable MCDA methods for our approach. And for example, we define that we want a ranking of alternatives and also that our metric values are all quantitative. And now as a first approach, we support the MCDA methods TOPSIS, Promethy 2, and Electri 3. So well, now our approach is as follows. So first of all, we have the user with its input circuit, and then the circuit is translated into the formats required by the supported quantum compilers. So for example, the Qiskit transpiler does not support QUIL as compilation or input circuit. And then we compile the translated circuit on all available quantum computers of supported vendors. Then the compiled circuits serve as input for the analysis, where we analyze the previously collected metric values about the circuits and also the quantum computers. And then in the next step, the analyzed metric values are handed over to the prioritization. So there, the user selects what MCDA method should be applied to calculate a ranking. And then finally, a ranking of the compiled circuits is presented to the user. Now the user can manually select what compiled circuit should be really executed on the target quantum computer. And then the results are finally returned. And in addition, in parallel, the execution results or the compiled circuit is also executed on the quantum simulator, such that we can evaluate the quality of the quantum computer results. So therefore, we use then the histogram intersection by superimposing the execution results of the quantum computer with the execution results of the quantum simulator. And then finally, the user can see all the collected metric values and also the measurement results and histogram intersection values. And then he again can adjust the weights that were previously used and, for example, can again rank the compiled circuits based on their requirements. So now the system architecture is as follows. So on the left side, we have the translator that we use or that we developed in previous work. And we also have the SDK services that wrap the compilers as well as the executors itself. And we also have QProf, our provenance system that enables the collection of up-to-date information of available quantum computers. And then the approach for the prioritization is based or is integrated into the NISQ analyzer, a tool that decides the executability of compiled circuits on quantum computers. So the approach is as follows. Here, the prioritizer invokes the performance extractor, and the performance extractor then prepares the metric values as well as the defined weights of the user. And then, we want to apply an MCDA method, and therefore we integrated a project called Decision Deck that provides MCDA services offering MCDA methods and these are callable via SOAP. So the prioritizer takes the prepared data and sends it over to the MCDA service that supports the MCDA method selected by the user. And then finally, it returns a ranking. It is stored, and the ranking is also presented to the user. So we also have some results. So first of all, I want to present you our user interface. So the user is enabled to create or add the implementation, what they want to analyze. So then with the given implementation, the user can start the analysis, and thereby he selects the vendor he wants to regard, and also can select the quantum compilers that should be considered for the compilation. And then the user can start the selection, and in the next step, as soon as the compilation and the analysis is finished, a list of compiled circuits is presented. And now this prioritization approach starts by selecting the MCDA method the user wants to use, and also set the weights for the different metrics. And therefore we use the method called SMART. So the user has to assign points between 0 and 100 to the different metric weights, but whereby 0 is of low importance and 100 is of high importance. And then in the background, the points, so the weights of the metrics are calculated by the point number of the metric divided by the sum of all points. And then in the background, as soon as the prioritization is finished, we have a ranked list of compilation results for the different backends. And now the user is also enabled to finally execute the quantum circuit, and also the histogram intersection is presented, and well, he can see the execution results. So we wanted to further support the user by defining initial weights regarding fast and stable execution results. And so we started a small case study, and therefore we considered the different backends of IBM Q, with also using the Qiskit transpiler and the TKIT compiler. And as I mentioned, it's the first approach. We use the three different input circuits that result in 21 compiled circuits. And so here is an excerpt of compiled circuits of one input circuit. So on the left side, we here have the metric values regarding the compilation results. And on the right side here, we have the metrics of the quantum computers. And additionally, we also executed the compilation results. And here we already have a ranking based on the histogram intersection values. So our first weight that we wanted to define was regarding stable execution results. And roughly speaking, so we decided that metrics that roughly reflect the ranking, the target ranking, they get the highest weight. So for example, here with multi-qubit gate depth, then again applied with the SMART method. And all other metrics get respectively lower weights. And now here we applied it on TOPSIS and Promethe. And as you can see, it roughly reflects the target ranking. In addition, we also wanted to consider the Q sizes. So in this case, the Q as the waiting time metric got the maximum weight, and the resulting ranking looks like follows. So as you can see, for example, here the Manila quantum computer or the compilation on the Manila quantum computer has now a much lower ranking, as it has the highest Q size. So, well, as you've seen, these initial weights, which we did manually roughly reflect the target ranking, but the user is enabled to prioritize based on its own requirements. Further, monetary metrics are not yet considered, but well, it's an expandable and plugin-based system, so further metrics can be added. And in addition, the comparison with the simulator results are limited because of the limitations of quantum simulations, but well, other evaluation methods can be added. And last, well, the Q sizes, we regarded that they do not reflect actual waiting times, so we have to consider further waiting time metrics. And well, in the future, we want to automate the learning of weights based on the past execution results, and also want to support the sensitivity analysis to evaluate the stability of the rankings. And for sure, we want to add further metrics and also further evaluation methods. So thank you for your attention. Are there any questions?
Thank you very much for interesting talk. So, are there any questions from the audience?
I can ask a quick question.
Yeah, please.
Yes, so I was wondering that, yes, it's a very nice piece of work in terms of collecting these metrics and evaluation methods. But I was wondering that is there any possibilities that we can use these metrics can be comparable to each other in terms of the, I mean, because I find that if they're a good set of metrics, but what do you think how they can compare to each other so that we can have more comparative analysis?
So you mean how we could compare the different compilation results based on this metric set?
Yes, exactly.
So I will. I had to search my mouse. So for example, here we can see that, especially as you may know, the multi-number or the multi-qubit gate are especially error prone. And so in general, it is considered that the number of multi-qubit gates or the multi-qubit gate depth has to be as small as possible. And here, as we see the ranking, for example, you can see that it should be as small as possible for a good execution result based on our initial weight set, to be safe. So does it already answer your question, or?
Yeah, I was thinking across the metrics, maybe. I think that I understand for each metrics when we see different numbers. So I think I understand that part now. But if I have to compare the two, for example, are there any relationship between the metrics? Or for example, let's say in the first row, we have the depth 14. And then we have total number of operations 21. And width is 3, for example. So I was just wondering, is there any way we can use this to, are they comparable across somehow, or they are independent of each other?
Well, we've seen that there is a dependency between the different metrics. So for example, regarding stable execution results, the user should not only consider, for example, the multi-qubit gate depth, but also, as an example, the decoherence time of the quantum computers. And also, well, the depth is an upper bound of the multi-qubit gate depth. And also the total number of operation, for example, shows that, the number, it's important to consider them. And also the splitting regarding not only considering all gates, but also only the single qubit gates and the multi-qubit gates.
All right, okay, thank you.
So I'd be wondering, how do you make sure that results are actually the same?
So you mean in regarding the histogram intersection?
So you said before, okay, so we need to check if results are the same when executed on different platforms and so on. But for instance, for D-wave machines, you will more or less never have the exact same result twice. So do you employ any similarity criteria? Same for D-wave. How do you decide that if two runs produce identical outputs?
So currently, as I mentioned, we are just using the simulator results as the way to be, and then we compare the simulator results with the quantum computer results, so that the error is filtered, so to say.
Okay.
Yeah.
If I may, I would also add a question on pricing, because the providers have different pricing models, and some have a 1 month. So IBM in Germany has the system of you buy a ticket and it's valid for 1 month and then it expires. And I would assume that once you bought a ticket, you're kind of locked in with one provider for that month, because you might not want to spend the money to buy a second ticket with somebody else. Tickets are really expensive. Are you counting, or are you thinking of taking pricing into account in this ranking?
Yes, as you mentioned, well, it's really a difficult task, especially regarding different providers. So for example, Amazon Bracket just pays for each shot, and IBM has these tickets. Yeah, well, that's future work, I would say, but yeah, it's really difficult task. Also, you have to estimate in advance what will be the costs if you run it on this machine or on the other. So yeah, we have to find it out.
Thanks.
You're welcome.
Okay, so thank you. Are there any other questions? Okay, if not,
maybe just a quick
yeah,
question.
please.
Thanks for the very interesting work. If I want to know more details about this work, so what is there any article like summarizing this work, or it's best to go to GitHub or like the README file?
So regarding the overall work, or just
the overall thing, like the presentation.
So well, this topic regarding prioritization is the to be published paper, and yeah, here you can see, for example, the previous work, which all build on each other. So for example, this NISC analyzer is, well, first initial paper about the overall framework, but then we added another work about the qprop for collecting current metric values about quantum computers. And we also had another paper about the comparison of different quantum compilers, seen here.
Okay, thank you. Yeah, I think that's good points to look into. Thank you very much.
You're welcome.
There is another question from Maya.
It's maybe just an understanding question. How strongly do you consider the waiting times in the queues, for example, with IBM Q?
So currently we, as I mentioned, for the approach of initial weights, we set the queue size comparatively to the others to maximum weight, and so it's maybe more 50 of queue size and 50 of all other metrics, but the users enabled to decide on their own if it should be considered and how much it should be considered regarding queue size.
Okay, thank you.
Okay. So thank you, Mary, again. And I think this concludes the paper session. And